Hello everyone and welcome back to another video. Now in this video we are going to talk about processes. Uh, this video is again a part of the Linux Masterclass course as well as the Web Development course. So as you can see in front of your screen, the Linux Masterclass course and the Web Development course are available on my YouTube channel, and the link to these playlists would be in the description below. So if this is the first video that you are watching, then I'll recommend that you start from the very beginning if you want to understand Linux. And in the last video we of the Linux Masterclass course, we talked about how user management is done and how permissions work in Linux. Very important topic, especially if you're pursuing to become a system administrator. So or anything related to DevOps or stuff like that. So very important video in those aspects, might help you somewhere down the line. So good to have knowledge, right? And without any further ado, let's get started. So at the end of the last video, the last thing that we covered was how permissions are managed for a process, right? And that led us to a question that what exactly are processes? I mean, throughout this entire series, we have been talking about, different processes, Daemon processes and things like that. So what exactly are these processes that are so essential for a system, right? So let's talk a little bit about processes. Right. So processes are just programs that are running on your machine. Right. These processes are generally managed by the kernel, and each and every process has a process ID associated with it. Right. So each and every process is going to have a PID, which is short for process ID, and this process ID is what the kernel is going to use to identify the process. Right, just how there is UID for identifying users, there's group ID to identify, GID to identify different groups. Process ID, PID is something that is used by the kernel to identify the process. Now to check all the processes that are running on your system currently, you can simply go to the terminal and simply type a command ps. If I press enter, I can see this text that just came in front of my screen, and it has two entries as of now. One is for bash and another one is for ps, right? And it has about 4 columns. So let's try to understand what these columns are, right? The first column, as you see in front of your screen, is the PID, again the process ID of the process, right? And let's write it down. So if you, let's say, run the ps command, then it will give you the following, right? The first is going to be the PID, the process ID, right? The second one that we see in front of us is a column known as TTY, right? With similar values in both the fields, PTS and then a forward slash and then a 0, right? So the second column is a TTY. TTY is generally the controlling terminal of the process, and each and every process, most of the processes that we run are associated to a terminal. So the ID of the terminal is written in the TTY, right? So this is simply the controlling terminal. And the value that is it has, PTS and then forward slash and then a 0, right? We'll understand about this value in a bit more detail later on, right? So don't worry about that. The third column that we have is time. So we have a time, and this time is simply the total CPU usage time this process is taking, right? So this is the CPU usage time, right? And then we have a fourth column, and the fourth column is simply the CMD, right? So it is simply a CMD, or you can also say a command, and this is simply the command that you are running currently, like the name of the executable or the program that you are trying to run, Now don't worry if you're not able to understand at this point of time what this fields might actually mean, what is a controlling terminal, or what is the CPU usage time per se. Don't worry about all that stuff, because we are going to get in a lot more detail about all of those things. But before we do, let's look at a very famous command called psaux, right? So if I talk about psaux per se, right, I'll write it down here, right? So if let's say we discuss about ps and then aux, this command, right? So it has these three, you could say, flags, right? So it has these three flags. First is a, the second one is u, the third one is x, right? Now whenever you run the ps command, it would generally show you only the processes that are usually ran by you, right? So this a here means that you want to see all the processes, right? Doesn't matter if it is being ran by someone else or some other user that we have in our system. It doesn't matter, we just want to see all the processes that are running in our system. So a stands for that, right? Now if you talk about u per se, U generally shows more details about the process, right? So it usually shows you more details about the process, because there can't be just four fields associated to a process, right? The PID, TTY, and time, CPU usage time, and what the command or the program was, right? So there are a lot more details associated with each and every process, and it gives you a lot more detailed stuff, just like we used to do the ls and then hyphen l, which means we want a long list of all the uh, directories or files that we have, and want to see a detailed look about the permissions and all those stuff about those directories and files. This will give you more details about the process. And x simply means that you want to list down all the processes, even the ones that don't have a terminal associated with them. So just to understand this for now from a layman's point of view, currently I had a terminal open like here, and I wrote the ps command here, and I saw these two things, right? So the first entry is for bash, and as I told you in the first video itself, that the terminal, most of the terminals and most of the distributions of Linux use bash by default as their main shell. That bash is the programming language that is used by the terminal in most of the distributions by default, right? So as I already told you about that, inside of bash we just executed another command or another program that is known as ps, so that gives us our second entry, right? And since both of these commands are executed like inside this terminal only, the one that I've opened in front of me, then both of them have the same value in the tty, right? Now let's say that I open another terminal, and to simply open another terminal I can either do a control alt t, right, which is going to open another terminal for me, or if I want to have another window here, I can simply do a control plus shift plus t. This is going to give me another window. I'll increase the size of this as well, and to toggle between the two windows from the keyboard itself, you can just do alt 1 or alt 2. So alt 1 brings me to the first window, alt 2 brings me to the second window, right? And if I again do the ps command here, I can see that this time it gives me pts/1 for both the commands, for bash as well as ps. Why? Because this one was the first terminal that I had, denoted by a 0, right? And this is the second terminal that I have, denoted by a 1, right? So all the commands we generally execute are associated with a terminal, a controlling terminal, right? But there are some commands that just run in the background. They are not ran through a terminal, but they still are running, right? There are some processes behind the scenes, majorly the daemon processes that we talk about, right? So this will show us, x will show us all processes that don't have TTY associated. Right, so they don't have a controlling terminal associated with them. Now let's try running this command, right? This psaux, right? I'll just quickly clear this up, right? And I'll close the second one, or I cleared the second one. I'll quickly run the psaux, right? And I can see that now this time around I can, probably see a lot of processes that are currently running in my system, and a lot of fields as well. So again, let's try to understand these fields one by one, right? So the first is the user field, right? So let me scroll down a little bit. I'll again write ps aux here because this is the command that we ran. And the first is user. Simply, who is the user that the process belongs to, because process also has an owner, right? So if we can see, most of the processes that are running in my system at this point of time are controlled by root. There are some processes controlled by system md, and again there are some processes that are controlled by me. So you will see that I also have processes in the name of Google Chrome. So all the processes that the Google Chrome is using currently, because since I'm using xcalidraw on my browser, right? So all the processes that the Google Chrome uses to run are also being controlled by me, right? So user generally shows you the owner of the process who is running it. The second field that we have is simply the PID. Again, I don't have to explain it. This is the process ID, right? The third field that is there is simply a percentage CPU. Now this percentage CPU is simply, as the name suggests, means how much percentage of the CPU is your system currently using, right? So earlier I told you that there is a field called time, right? And this time simply means the CPU usage time, right? Like how much, time is the CPU giving to this process to run this process, right? And if it is very low, then it generally doesn't have uh, a value per se, right? But later on you will see that you have are generally starting to get some processes that are showing you some values in this field. So you can see that this genome shell that I'm using, the CPU is usually generally giving it about 60.1% of its time at this point of time, right? Then there is this one process known as Chrome. Chrome is currently taking up about 5.8 plus 0.8 plus 0.5 and whatever it is. I mean, whatever the number comes up, that is the percentage of CPU time that my Chrome is currently using. And there would be some other processes who are also using some significant percentage of time that the CPU has, right? So this simply gives you the percentage of CPU time that is being used by any process, right? The fourth field that we have is again an interesting one, and this is the percentage mem, right? Again, as the name suggests, what it should be, this is the percentage of memory that the process is taking, right? And this is simply the percentage of memory that the process is using out of the entire physical memory that I have in my system, right? So again, you will see that a lot of processes are taking negligible memory, so they are generally coming as 0.0, right? Negligible percentage of memory. And then there is this one Chrome that is using about 1.3% of my memory right now, right? And again, there is Chrome that is using, a lot of processes of Chrome are using a significant percentage of memory out of my system. And genome shell that I'm running right now, right, which Ubuntu generally defaults to, is also using about 1.2 percentage of the memory that I have in my system. I have around 16 GB of memory in my desktop right now, so it is taking 1.2% of that. So that is the percentage mem field. Then we have a VSZ and an RSS. Right, we have these two columns. One is the VSZ and the other one is the RSS. Right, so let's write them down. The first is VSZ and the sixth one is RSS. Right, so what does this VSZ and RSS usually mean? Now this VSZ is simply the virtual memory usage of the entire process, right? So all the processes have some VSZ allocated with them, and you can see that the first process itself with a PID of 1 has a lot of memory usage, the virtual memory usage. And by that I simply mean that when this process was initialized, right, when this process started up, this is the amount of memory that was allocated to the process. Right, now if this process wants, it can use the entire memory that was allocated to it, or it can use some portion of it, but it cannot use more than that. Right, so here you will see that when this process was initialized, it had this much memory allocated to it. So if it wants out of this entire memory, right, so if it wants, it can simply use this entire memory, but it will not be able to use any memory more than this. Right, this was the maximum amount of memory saved for this process. That if this process wants to use more memory, if it is requiring some more memory, maybe performing some stuff or things like that, then the maximum amount of memory that it has reserved for this process is this amount. Right, and as you might have guessed by now, RSS is simply the amount of memory that it is using, like actually using. So this is like the memory that is reserved for the process, that was allocated to it, that if you want to run, then this is the maximum memory that we can provide you. Right, and this is quite an important process. We'll talk about this init process later on, but this is the maximum memory that was allocated to the process, and out of that maximum memory that it can consume, it is currently just consuming this much amount of memory. Right, so this is the maximum memory available to the process. Right, and this is what? Memory currently used. Right, so VSZ is simply the maximum memory that is available for the process to consume if it wants to, and RSS is simply the memory that it is currently using. So we can simply say that VSZ is always going to be greater than or equal to RSS. Right, and these memories that are here are always written in KB. Right, so if we talk about this number here, then it simply means that it is currently using 13,340 KB of memory out of the 16 GB RAM that I have in my system. Right, so that was the VSZ and the RSS field. Now we have the field that we are already familiar with, which is the TTY field. And you will notice that this TTY field, in majority of the cases, either has a question mark or something known as a TTY2, or as we saw in the earlier example, something that resembles this, a PTS and slash a 0. Right, so it has these three types of values. Right, now we are going to talk about what this PTS and this TTY actually mean. Right, but whenever the value is a simple question mark, right, like in majority of the processes that we have in front of us, whenever the value is a question mark, this question mark simply means no terminal associated. Right, now we have another column known as stat. This simply means what is the status of the process. Right, so stat which is simply the status of the process, right? Then we have another field called start, right? Start, and it's self-explanatory. It simply means when did I start this process, right? At what time did I start this process? Now then we have the, the fields that we are already familiar with, the time and the command. So we'll just write it down, but won't again go to the explanation. Time and command. So these are roughly, all the fields that are there whenever we execute the ps aux command. And as we may notice that, when I executed this ps aux command, or when I, let's say, execute the ps command, I can see that it, just tells me about whatever the processes are running, right? And it just kind of gives me a snapshot of it, like what are the processes that are running, right? And this gives me the snapshot of the point of time where I exactly like ran this command. But if in case I want to, see the real time data of what is happening with all the processes that are running in my system, then I can simply I'll just clear my terminal and I can simply write a command called top, right? So top is a command that, just gives me the psaux version of the kind of psaux version of the entire, the process with some fields here and there. And it is going to give me the real time data. So as I can see, this data in front of me currently is, just fluctuating a lot. So that is there. And I can, if I let's say want to toggle this, I can simply use the arrow keys, right? If I want to quit this, I can simply press the Q, and this Q means quit, which is going to quit the tops interface and bring me back to my terminal, right? So that's, the top command that is there for viewing the processes in a real time. This top command is, usually used to see, what processes might be slowing down your system, or affecting your system in a way that it's hanging a little bit or things like that. And by default, this top command that is there, it refreshes in about, 5 to 10 seconds, something like that. Now let's talk a little bit about the controlling terminal that we have, right? So we saw two types of, terminals. So let's talk about controlling terminals. And if you remember, we saw about two types of terminals. One was something that was in this format, tty, and then some value, let's say 1, right? And the other one is in this format, which is a pts and then /1, right? So we saw these two types of terminals when we were looking at the ps aux. Now this tty that is there, this is a regular terminal, and this pts that we see, this is a pseudo terminal, right? So you might be wondering what is the difference between a regular terminal and a pseudo terminal. So a regular terminal is something that has no graphics associated with it. It is simply just a shell. You cannot do anything inside of it except for just, there is no mouse, nothing. You cannot do anything inside of it except of just using your keyboard to type your commands, right? That is a TTY. And I cannot show you an example of TTY right now because the software that I'm using to record my screen, I just the inbuilt software that I'm using to record my screen, I just checked that whenever I try to access the regular terminal, then it is not recording the regular terminal, but it just stays on the GUI part of my desktop. But if you are using Ubuntu, right, then you can simply type control plus alt plus F3, right, and that will lead you to your TTY3, right? So F1 is for TTY1, F2 is for TTY2, F3 is for TTY3, the terminal 3, F4 is for terminal 4, so on and so forth. And these terminals in your system, they might have different values, and they might be associated with different keys as well. So for my Ubuntu that I have in my system, the control alt F1 leads me to the home page directly, where I have to type my password to log back in, right? The control alt F2 helps me in exiting the terminal, the TTY terminal that I can enter. And my terminal in my system, it starts from control alt F3. So if I type control alt F3, then it is going to lead me to the TTY3. And if I type control alt F4, it is going to lead me to TTY4, so on and so forth. If I type control alt F7, it is going to lead me to my TTY7. And if I want to exit that terminal, I can simply do a control alt F2. That is how it is configured in my system. It might be different in your system based on whatever distributions you are using and things like that. So before trying to access regular terminal, if you want to, right, before trying to access them, just make sure to check in your system, right, that from like whatever distribution you're using, from what are the controls to get inside of a regular terminal, and what are the controls to exit out of a regular terminal. Because if you get stuck, then you might have to again search the browser that I'm using this distribution, and how do I exit. This is how a TTY looks like just to show you an example. This is not exactly what I'm running on my system right now, since I couldn't record it, but this is just a snapshot of how a TTY goes, like the actual TTY goes. So this is how a TTY looks like, and as you can see in in front of your screen, there is no GUI element to it. It's entirely command line based, right? And that's when the pseudo terminals comes into picture, the PTS/1, which is the regular terminal that we open or we have been working with. This is a pseudo terminal here, and that's why whenever I do a PS, it shows me a PTS0. But if I do a PS aux and press enter, then I can see that there are some terminals that are running. So I tried to access my TTY3, which says that it is currently running bash, right? And yeah, that's pretty much it. There is also a process for logging in into the system, and that was also used by TTY3, because when you like go into your regular terminal, then you will first have to write your username, then your password, and then you'll get access to the command line terminal that is there, right? So so that is the difference between PTS and TTY. Now these processes that we have been talking about, they are always bound by a controlling terminal. So let's say that I am trying to run some commands in my terminal, and I just close the terminal, right? The process will also go with it, right? It's not like the process is going to remain there. I close my terminal, whatever processes that were associated with that terminal would also go along with that. Now we know that there are daemon processes, the processes that are essential to keep the system running, right? And they start when the system boots up, and they terminate when we shut down the system. Now these processes run in background, and since these daemon processes are so essential in making sure that our system is running fine, that we don't want them to close, that is the reason they are not associated with a controlling terminal. So all the processes that you see in front of you with a question mark, these are essential processes to run the system, and only because we don't want these processes to close down is the reason why they are not associated with a controlling terminal. Because if we, let's say, accidentally close the terminal that is running these processes, then our system is going to crash. Now a process is running a program in a system, right? And our system is allocating various things. It is allocating it some memory, some CPU, input output, and all those things, just so that it can run the program, right? A process is generally like an instance of a program that is running. So just to show you an example, let me do this thing. So I quickly open two more terminals, right, this and this, and let me increase the size of this as well as this, right? Now let's say that in this terminal I run a cat command, right? Just a simple cat command, and I press enter, right? Since I didn't give an input to the cat, it doesn't have anything to show me as the output, right? And similarly, I'll run a cat command in the third terminal that I opened as well, and again the same thing, it is not going to give me an output. But this time, if I simply do a ps and then aux, right, and with a pipe, which means that the output of this ps aux command is going to go as an input to the grep, and we want to grab cat out of whatever output we are getting out of ps aux, right? I press enter. I can simply see that I have a cat running in my sudo terminal 1 and a cat running in my sudo terminal 2, right? That I executed just right now at 1 minute ago. So I can see that I have these two things that are running along, and although they are both executing the same command, they are both executing the same program, which is cat in this case. We still have two instances of it, right? And if I, let's say, close this one, it is going to ask me to close. And if I close this one, and then I again do a psaux and then cat, then I can see that I don't have any instances of cat running anymore that are that are running in a pseudo terminal per se. Obviously they are running behind the scenes in the background, but they are not currently running in a pseudo terminal. So the only thing I get in a pseudo terminal is this pts0, in which I ran the grep command with the cat as an argument, right? The string that I wanted to find out. Right. So this proves that processes are just, the instances of the programs that are running. We can have as many instances of a program running in our system as we want. Now a question, that might pop up in our mind would be that who is deciding in this entire system what resources do we want to allocate to any of the process that is running? Because as soon as we run some process, it is going to require some resources, right? It is going to require some vsz value, which is the maximum memory that is reserved for that process to use, right? And it is going to utilize some cpu time as well, and things like that. So who is making all those decisions? Just think about it and try to come up with an answer for that. Who is like the one responsible for providing all the resources that a process might need? All the processes are trying to get some resources from the system, right? Now the kernel that we have in our system, the kernel that we even talked about in the first video, and we are going to talk about it later on in the in the Linux Masterclass as well. But the kernel that is there, it is responsible for all the processes that are there. And when we run up any program, when we run any command or any program that is there in the system, it is the kernel who loads up the code of that program in the memory. It then determines and allocates all the resources that that program may need, and it generally keeps a tab on all the processes that are running. It knows the status of the process, it knows who is the owner of the process, it knows how many resources are allocated, how many resources are received, how many resources are consumed by a process, things like that. It basically knows everything in the system, right? Now it is the kernel's job to make sure that all the processes that are running get what they need, right? So whatever the process is demanding, whatever resources it may need, it needs some this some much amount of memory or this much amount of CPU time or things like that. Whatever it needs, it's the kernel's job to ensure that it is receiving what it is demanding, right? Any process. Now when a process ends, if let's say I was using the cat command earlier on two different pseudo terminals, and I closed them, so whenever a process ends, it frees up the resources that the process was using, and then these resources are available for other processes to use. Now we are going to get into a little bit of theoretical part of how processes work behind the scenes, so bear with me, but this is a very interesting concept, right? So what happens when a process is created? So let's say that I had a process called ps1. Right. Now when I create a new process, it might be that this process is cloning itself to create a new process, and you know this cloning is done through something known as a fork system call. Right, and we'll study about system calls later on in the course, but for now just know that system calls are somewhat of a request that a program makes to the kernel of the operating system. Right, so these are simply just requests that a program is requesting that I want to do this. Right, so these are system calls. Now this fork system call creates an almost identical child process, and it assigns a PID to that, a process ID to that. So it will create a child process, right? It will create a child process and allocate some PID to it, right? This entire thing is done by the fork system call. Now the original one from which this child process cloned itself becomes the parent process. It's like the reproduction system, but in computer science, right? So it gave birth to a child and now it became a parent, right? Because the child is like cloned from it with a different PID. You can say that this is the name of the process, let's say. Now this child process can use, the same program that its parent was using, or in most of the cases, it could use the execve system call, right? So there is something called an execve system call through which it can run a new program, right? So it can choose to run the same program that its parent was using, or it can use the execve system call to run a new program. Now let's try to execute a command, right? ps hyphen l, right? I press enter here, and again hyphen l, what it means is I want to do like see a detailed version of all the processes. What you will notice here is that there is one more separate field that is called the ppid, right? So this is known as the ppid, right? And I can see that the ps command that I am now running, right, it has a pid of its own. It has a pid of 24942, right? But it has a ppid which is the parent process id, right? And it has a ppid of 5374, right? And now if you look at this ppid 5374, you will notice that this ppid 5374 is the id of the bash command that was there. So this 5374, this ppid of this ps command is the id of the 5374. So we can say that this ps command that we just ran is the child process of this bash command that we ran, this process, right? This is a child process of this process, this is the parent process, right? And again it has a parent process as well, right? Something in the system. We could try to see what it is using ps aux and then grep and then 5352, which is the ppid of this bash, right? I press enter and I can see that it is a child process of the slash user slash libexec slash genome terminal server. So the genome on which Ubuntu runs by default is the parent process of the bash that we ran, like that comes with the terminal. And then we ran a ps command which is a like the child process of this bash process, right? So if you look at the hierarchy here, we can, let's say that we had a genome process, right? And this became the parent of bash process, right? Which again become a parent of the PS process that we just ran, or the PS program, right? So this is the hierarchy. Now there is one question that we might be wondering: if every process has a parent process, right? If every process has a parent process and all the processes are just a fork of each other, right? Just because they are using the fork system call, right? Then there must be a process that is above everything. There definitely must be a process that is above all the processes, right? The mother process of all. Now this mother process that we are talking about is simply called the init process, right? Which is also known as the mother process. So when the system boots up, the kernel creates a process called init process, which is the mother of all processes, right? And this init process has a PID of 1, right? This one is the PID of the mother process, right? And now if you would, recall from what we saw earlier, if I do a psaux command, I can see that the first command, the first process that is there in this entire list is this process slash sbin slash init, right? And this has a PID of what? 1, right? So that is the reason it has so many virtual memory allocated to it, the the memory that it can use, right? And this is the very first process that gets created by the kernel when the system boots up, right? And this is the mother process above everything. Now this mother process, this init process, runs on root privileges because root is the owner of this process, right? So it runs on root privileges and it runs a lot of processes that are responsible for running the system, right? So all the systems, all the processes that are ran after that, right, they all are processes that you know were forked from the init process, right? And they are responsible for running the system, right? So here if we see, let's say this is the init process, right? It will create a lot of child processes, right? And all these child processes, they might have some other child processes associated with them, right? But all these processes, this entire list that we have that are responsible for running the system are known as the daemon processes. So these are the processes that are responsible for keeping the system running, right? And they are all just the forks of the mother process, right? Now we at this point of time understand what happens when we create a process, right? But what happens when we terminate a process? Now a process can exit using something known as an exit system call. Right, this is an underscore here. So underscore exit is the name of the system call. Exit system call is what a process can use to exit, and this system call is responsible for freeing up all the resources that the process was utilizing. Now when a process terminates, whenever a process terminates, it lets the kernel know why it is terminating through something known as a termination status. Right. So this termination status tells the kernel why the process is terminating, and the most common termination status that is there is the termination status of 0, which means that the process succeeded. So this means that the process did its job, and just because it's it has completed its job, it is now terminating, right? Then this is one of the most common termination statuses that are out there, that the kernel receives whenever a process is ending or a program is ending, you can say. Now coming back to the example that we were using. So when a process terminates, its parent has to acknowledge that my child process has terminated, because this is the parent process here, right? So if let's say their child dies, they have to acknowledge that their child has terminated, their child has died, right? So this parent has to acknowledge, and they can acknowledge the status of their child process by something. When let's say this terminates, then it is acknowledged by something known as the wait system call. So this is how the system usually works, right? This is how the entire system usually works, how a process is created, how it is terminated, what happens when a process terminates. But there are a few edge cases here, right, that we should discuss. So let's say we have a case, right, where I have a parent process and I have a child process, right? But in this case, instead of the child dying, the parent process dies or the terminates, right? Let's say this is the scenario. So what happens to this process here? What happens to this child process that we have? Its parent died, right? So who is this process going to belong to now? Now these child processes whose parent dies are known as orphan processes, right? And in this scenario, the kernel knows that whenever this child process will die, right, or whenever this child process terminates, it does not have a parent that is going to use the wait system call to acknowledge that their child has terminated. It knows that it does not have a parent that will use the wait system call to acknowledge this, child, the termination of this child. So what the kernel does is, let's say the init process is here, the mother process. What it does is, it places the child process under the protection of the init process, right? And this is the reason why it is known as the mother process. Well, I think this is the reason why it is known as the mother process. So the parent died, and the kernel knows that there is not going to be a wait system call from the parent, so it puts the child under the init process, under the mother process, and this mother process will call the wait system call so that the child can rest in peace. So this is usually happens when the parent process dies before the child process. Now there is one another case, right, case 2. Now again, let's say that we have a parent process, right? We have a parent process and we have a child process, right? And this time the child process terminates, but the parent process did not, call the wait system call, right? It does not want to acknowledge that its child died. What happens in that case? Now we still want to know how the child process terminated. We want to know the termination status of this child process, right? It could have been 0, that it succeeded, or it could have been something else. Something else happened to this child process due to which it terminated. We still want to know it, right? But the parent process is not calling the wait system call. So in this case, what kernel does is, it turns this child process into something known as a zombie process. So it turns this child process into a zombie process, that it's a living dead. It has already terminated, but it still exists because it has, like, the system doesn't know what was the termination status of this process. Now, if let's say when this turns into a zombie process, if let's say the wait system call is then called by the parent after it turns into a zombie. So let's say the parent calls the wait system call for to know the termination status of the child process, right? Then you know it is known as reaping. If the parent process still does not calls the wait system call, then again the init process that is there, this init process will adopt the zombie process that is there. It will adopt the zombie process, and it will then call the wait system call, so that the zombie process can again rest in peace, right? So that usually happens behind the scenes of the process. Now we know what happens when a process is created. We know when a process what happens when a process is terminated. Usually it's the parent who calls the wait system call. But as we discussed in case 1, if the parent dies before the child, then the kernel knows that the child process also has to die, so it makes it an orphan process. It gives that to the init process, and the init process performs the wait system call for the process. If in case the child process terminates and the parent process does not calls the wait system call, then the kernel makes it a zombie process, that it's not you know it's terminated, but it still exists in the system. It will still come up in the PSOX, right? And if the parent then calls the wait system call, then again the zombie process will disappear. But the thing is known as reaping. But if the parent does not want to acknowledge that their child has terminated, then the kernel puts the zombie process under the protection of init. Init adopts the zombie process, it performs the wait system call for the zombie process, and then the zombie process disappears. Now we have another important thing that usually goes with this processes, and that is known as signals. So signal is just basically a notification to the process that something has happened, right? It could be anything, and these signals are very useful for multiple things that usually happen. Whatever user presses control C or control Z to kill or interrupt or suspend the process needs to know that it has been killed or suspended, right? Only then will it happen. Maybe some hardware issue occurred and the kernel wants to notify the process. Maybe some software issue occurred and the kernel wants to notify the process that something has happened, right? So in those scenarios, signals are used. Now when a signal is received by any of the process, it can do a lot of things with it. The first thing it can do is it can ignore the signal. The second thing it can do is it can catch the signal and perform the signal handler routine. Whatever is configured how to handle a specific signal. There are different signals, right? And any process or program might have some signal handlers that are responsible for handling different signals, right? Maybe it could be that a software is running, and as soon as it receives a termination signal that it has to stop working now, or it has to terminate itself. Before terminating itself, let's say the signal handler of that process would save the data that that process has collected in some file and then terminate itself. So it could do a lot of things. The process can be directly terminated, you know as opposed to the normal exit that they usually do, where the exit system call is used to free up the resources in the system and things like that. It could also block the signal based on some signal mask. Processes usually have the signal masks that can be set to block particular signals. So there are different types of signals that are out there, and let's take a look at the common ones. So the first one is SIG HUP, right? It is also known as HUP, or it is numerically denoted by 1, right? This usually means hang up. We have a signal known as SIG int, also known as just int, denoted by the number 2. usually means interrupt. We also have a signal called sig kill, also known as kill, denoted by the number 9. Right, this simply means kill, as the name goes. We also have a signal called seg v, also known as just seg v, denoted by the number 11. This is generally the segmentation fault. Right, we have one more signal called the segterm, or just term, denoted by 15 numerically, known as terminate. Right, and we have one more signal called the sig stop, or simply stop, denoted by the number 19. This is simply to stop. So these are the most common signals that are there, and since we talked about signal masks, how they can be set to block a particular signal, some signals are unblockable, right? So for example, this sig kill that we have, this signal cannot be blocked no matter what, and it simply just destroys the entire process. Now there are a lot of processes running in our system. We can usually check all the processes that are running. Now it might be that we want to kill a particular process. We don't want to want it to run anymore. So what we can do is we can simply call a command, use a command known as kill, right? And after kill we can just enter some process id, like some random process id, whatever the process id that process might be having that we want to kill, right? And this kill command by default sends a termination signal to the process, after which it will call the the exit system call, and its resources would be freed up, and it will be available, the resources would be available to be reallocated and things like that, right? So we can use this kill command to kill any process, and by default it sends a termination signal to any process. But let's say that we wanted to not send the termination signal, but we instead wanted to kill it entirely, or maybe do some other thing with it, right? So in that case we can simply do a kill and then -9, and this -9 simply means that I want to kill the process. So 9 is the number that is numerically represented. This 9 is the number that is numerically represented to kill any process, and if I do a kill -9, then it will, instead of terminating the process, it will kill the process. That means destroy it instantaneously, but its resources might not get freed up, so the kernel would have to do it later on. So that's how we can kill any process that we want to, through different signals that are there. Now all these signals kind of look very similar in nature. So what is the difference between these signals that we see in front of our screen? So the first signal, the sig hub signal that is there, this is usually sent to a process when its associated terminal gets, or its controlling terminal gets closed, right? So then we simply mean that you have been hung up, right? I mean, the terminal that was controlling you was closed, and you don't have any medium to work anymore. So that is usually the signal that the process receives when it is running in a controlling terminal and the terminal got closed. Now the sec int that is there, it tries to gracefully kill the process, and whenever we are running something, if let's say I'm doing a cat here and I press a control C, then this control C means that I am interrupting the process, right? So that's usually the interrupt. Sick kill is like just killing the process, that just destroying the process, and there's no cleanup after the process is destroyed. Its resources might remain still unaccessible for other processes to consume or things like that. Sick term is again to kill the process, right? But after doing some cleanup, right? Like we wanted to free up its resources and things like that, and then we want to kill it. So that is simply sick term. Sick stop simply suspends any program for some time, right? And then it might start resuming after some time. So it simply stops the process. And this segmentation fault signal that is there, it generally occurs when the process it is trying to access some area of the memory that it does not have access to. So if I do a cat here with the /etc/sudo, sorry, /shadow, if I enter this command and I press enter, it gives me a permission denied. So it like wasn't able to successfully execute what it intended to, right? It got you know uh, terminated before even it executed the entire thing. And this process, while executing, would have received the segmentation fault signal because it was trying to access something that it does not have permission to do. And if I simply do a sudo before this, then it will execute after obviously entering the password, right? So this is usually the difference between different signals that you see in front of your screen. Now, when you run multiple processes in your system, you've run multiple things. At this point of time, I'm currently running a terminal. I'm currently running Google Chrome. I'm also, currently running the screen recording software that is recording my screen, right? So it seems like, all of these processes are running at the same time, right? But that's not the case. So these processes that are running currently, the Chrome and the screen recording and the terminal, all these processes usually use the CPU for a small amount of time, right? And that is known as a time slice, right? So these processes use the CPU for a small amount of time. So to understand this, let's say I have three processes, right? I have this PS1, I have this process called PS2, and I have this process called PS3, right? So this process is going to, and let's say that this is my CPU, right? So this process is going to use it for a small amount of time, right? Probably some milliseconds, right? It is going to use it for a small amount of time. Then this process is going to use it for a small amount of time. Only one process can use you know the CPU at a time, right? So this is going to use it for a small amount of time, then this is going to use the CPU for a small amount of time, and these small amounts of times that are there, they are usually the time slices that we are talking about. And once the CPU has given time to this, it has given time to once the CPU has given time to the process 1, it has given time to process 2, it has given time to process 3, then it is again going to give time to PS1, and then the cycle continues. Then it is going to give time to PS2, and then it is going to give time to PS3, right? So this process continues, and again from here it will again give time back to PS1, and so on and so forth. So it will keep going on like that. These processes, once they get their time slice, they usually pause for a very small amount of time, milliseconds usually, and that time allows other processes to use the CPU for again for a time slice, for a short time slice. And this usually goes in a round robin fashion. It first would give some time to PS1, then some time to PS2, then some time to PS3, and then again to PS1. And that is just in this example. Usually all the processes that are running in the system are taking some time of the CPU. So whenever we do the PS command, when we see this, time that it is using, right? Or if I do a ps aux, right? And here, whenever I see how much time anything is using, then it usually means that it is giving about this much amount of time to this process, right? Out of the entire time that it has, right? So that's usually, how it goes. It's giving this much amount of time to this process and almost negligible to a lot of other processes. And that is why, whenever we buy CPU, we, usually see that, our processors might have multiple cores, right? There are processors with dual core, there are processors with quad core, there are processors with octa core, right? 2 cores, 4 cores, 8 cores, things like that. So the more cores a CPU has, the more processes it can run simultaneously, right? Because the cores are responsible for providing these time slices to the processes, right? And if let's say that there are about 100 processes running, right? Let's say there are about 100 processes running, and your CPU has about 4 cores, right? Then this means that one core is handling about 25 processes at the same time. And then I mean this time is normally equally distributed, right? It is normally very equally distributed. Might be a little bit here and there, but generally it's equally distributed. All the time slices are equally distributed. Now all the processes, they usually get enough time slices to finish executing, right? Finish processing. The kernel, usually handles all the switching between the processes, right? Like where's the CPU's time going, it is entirely handled by the kernel. So that's, what usually happens when we say that kernel is the one controlling the hardware and helping it, interact with the software. Then that is what we mean. I mean, the kernel is responsible for memory management. It is, as you see, is also responsible for, making sure how much processes are receiving how many time slices, switching back between different processes and things like that. So it's like doing a lot of stuff. So kernel is basically like the CEO of a company. The computer is the company, right? And the kernel is the CEO of that company, and it is managing, all the resources, what CPU goes where, what memory goes where. Processes are like employees, right, working for the company and things like that. So you know that's how it usually works. And the more number of cores your CPU has, the better it performs. The only reason being is that since the CPU can only give time to one particular process at a single time, then if let's say a lot of processes are running in on your system, and your system, your CPU usually only has one core, then it might be pretty heavy for that one core to manage so many processes, right? Giving time to so many processes, and the performance might slow up because of that. So that's what usually happens. And the kernel, happens all this switching between the processes for different resources. Now these processes cannot decide, how much resources they will get. They cannot decide how much memory they are getting. They cannot decide how much CPU time they are getting, because if they get to decide, then they'll want to keep everything by themselves. They wouldn't want to share it with others, right? So when these processes, behave normally, then roughly they all get about equal amount of time slices. But there is a way to, influence this kernel's, process scheduling algorithm. There's a way to influence that through a value known as nice, literally known as nice. Now all these processes that are running in the system, they have a number to kind of, determine the priority for the CPU, like how much priority the CPU should give them, right? So they usually have a number. If I, let's say, clear this up and I use the top command, I can see another column known as ni. right? This ni column, and this ni column, all the values that are here, this 0 0 0 0 and then some minus 20s, and if I, let's say, go down, I would see some other values as well, like 19 and a 5 and things like that, right? So these are generally, the values that tell the CPU how much priority they should give to a particular process. And a high number, a high ni number usually means that the process is very nice. So if, let's say, we are talking about this process per se, which is tracker extract, then it means that the process is very nice. So this nice value represented generally by ni in the top command, right? So high value means low priority, and opposite to that, low value simply means high priority, because the CPU knows that this process is not very nice, and it has to butter up the process to, just so that it performs, it performs well, kind of that kind of a thing, right? So high value, if the nice value is high, then it simply means that the CPU does, should not prioritize this process because it is already nice. But if a process, let's say, has low value, then it tells the CPU that this is the process that is not acting very nice, and it needs a lot of your CPU time, so you need to spend more time with this process, right? So there are two ways to influence the nice value of any process, right? And there are two cases as well. The first case is that there are different set of commands and programs that are available to you, right? So if you want any particular program, right, to execute very fast, right, then you can probably, you would probably want to change its value, the nice value, that whenever I execute this particular command or this particular program, I want it to have a lot of CPU time, and you might want to set its value very low. So we saw that minus 20 was a value in the top command, so we might want to set it as minus 50 or something, that leave everything else, this is the process that needs a lot of time, right? It might be that you're scraping some website or something like that, and you want it to execute very fast, so you would want your CPU to give more time to this program so that it just executes it as fast as it can, right? So in those scenarios, when you want to change the nice value of a new program that you might execute, right, then it's simply done with a nice and then hyphen n, and then the value whatever you want to set it, like give it to, I could give it 10, I could give it minus 50, I can give it whatever I want, right? So value, let's say the value is minus 10 for now, I want it to you know be a higher priority for the CPU, and then I simply do whatever the command is. It could be cat, it could be a program that I wrote on Python, whatever it is, right? So this way I can influence how much CPU time my program will get, and it might execute slower or faster relatively based on that, right? So that is one way of doing it. If, let's say, a process already exists, right, it's already running, and for that process you want to change the nice value, then you can simply do the renice command, right? See, renice is a program to influence the nice value of the processes that are already running. So you can do a renice. You can tell what you want the value to be for the nice. It's, in this case, I want it to be minus 10, right? And then you do a hyphen p, and then just simply enter the PID of that process, like whatever processes nice value you want to increase, that process will be having a PID, process ID. You enter that process ID here in this command, and this 10 is going to be the value that you want to keep for that process, and it's going to change that accordingly, right? So that's how it usually works. Now let's quickly talk about the process states as well. We saw that the processes have some states, right? So states of a process, right? So the first state that it has is an R state, and this R state usually means that it is the process is running. Right. This R states usually means that the process is running and it's wait or it's waiting for the CPU to give it time to process. Right. So that is the R state. The second state that is there is the S state. This means running or runnable. Now this means interruptible sleep. And by interruptible sleep, it usually means that it's waiting for something, for some event. If it might be that you know you are running a program that is waiting for an input in the terminal, right? An input from the user, then that is in the state of S, right? That process, that program is in the state of S. It is waiting for an event. It is waiting for the user to enter an input in the terminal, right? The third state that is there is the D state. Opposed to S, it is the uninterruptible sleep. Now these processes cannot be killed or interrupted just by a signal, right? There are some processes that usually do not get interrupted. You cannot kill them, you cannot interrupt them, you cannot do anything with them. If you get stuck with any of these processes, usually just reboot your system, right? That would automatically end it, right? The fourth step, the state that we have for the processes is the Z state, simply for zombies. The zombie processes, and these are terminated processes that are waiting for their wait call status to be collected. So their parent did not call the wait call and did not collect their termination status, so the kernel has given it to the init process, the mother process, and the mother process will call the wait call and collect their termination status, report it back to the kernel, right? So that's how it is. And the fifth state that is there is the T state, which simply means stopped. So this process is stopped. So these are the states of the processes that are there. And now remember that in the very first video of this Linux Masterclass, I mentioned that in Linux, everything, each and everything that is there is simply a file, right? So processes are also a file, right? In the home directory, in the root directory that is there, if I, let's say, do an ls and then a slash and then a proc here, then proc is the directory that contains all the information about all the processes that are running in the system. I do an enter here, I can see that currently there are a lot of processes running in the system. All the subdirectories of this proc directory that is there, all the subdirectories, they are just the process IDs of those processes, and these directories with the name as the process ID, these contain information about the process, right? Whatever, this ID, whatever process it belongs to, it will contain information of that process. So I can easily go to cd slash proc and slash one, right? One is the mother process, the init process that is there. I can do an ls here and I can see that you know there are some things that I cannot list down because I don't have permissions for that, but other things I have, right? And I can simply view the status with a simple gedit, and status. I press enter and I can see that this is the status of the mother process, the init process that is running, and it has a lot of information inside of it again, but let's not get into all these details because that is going to take ages, right? But it usually contains a lot of information about all the things, all the system calls that this mother process can make, and things like that. What is the personality of this mother process? Right, there are a lot of things, the command line, and things like that. So it usually gives you a lot of information about each and every process, and each and every process, like information that is available for any process, is in the form of a file. Right, so when we say that Linux, everything in Linux is a file, we mean it. Right, now this proc directory that is there, if I do a cd dot dot here to go into the parent directory and I do an ls here, so this proc directory that is there, this is usually the directory from where the kernel sees the system. Right, so the kernel, it's not like the kernel sees each and everything that you're doing in the system. All the processes that are running in the system, they are saved here in subdirectories and files and things like that. And whenever the kernel wants to see what is happening with the system, or what process does it needs to give some time slice to, some cpu time slice to, it wants to schedule the time slices for different processes, switch the processes and things like that, allocate some resources, take some resources from the processes, whatever it is, whatever the kernel is doing, it is taking all that information from here, from the slash proc directory. Right, now let's talk about one more thing, one last thing about this video. Right, I'll go back to my home directory, and what I'll do is I'll create a new file. Right, I'll create a new file called test.py. Don't worry, I mean, this is not related to this thing is not related to Python, but to show you an example, I want to write a program in Python, right? And don't worry if you don't understand what I'm doing right now. I'm going to simply import time. Time is a library to control time in Python, and what I'm going to do is I'm going to do a time.sleep. It is a function of the time library sleep, right? And I'm going to pass a value of 1000 into it. So if I pass a value of 1000 into this, then it means that I want this program to sleep for 1000 seconds, right? And yeah, that's exactly what I want to do. And I mean, you start this program, it will sleep for 1000 seconds and then it will terminate, right? So this is a very simple program that I've written in Python, and I can see that it exists in test.py. Now if I, let's say, try to run this program through the Python 3, right, Python 3 and then test.py, I press enter, I can see that this program has started running right now, right? But by the time this program is running, I cannot use the terminal anymore, right? So many a times you might be running some program or some scripts that are taking a lot of time to run, and you don't want to wait around for it to execute. You want to continue doing your job, right? And you want this program to run in the background, right? So for that, what you can do is I'll simply do a control C, and do know that when I did a control C, it says that I interrupted the program, right? And when I was telling you about the different status codes of a program, I told you that if you want to interrupt a program, a simple control C interrupts the program. So I control C it, and I can see that it got interrupted. Now if I want to run this in the background, what I can do is I can simply do Python 3 and then test.py, and I can add an ampersand after that. Ampersand is the shift and then 7 in the keyboard, right? So this is also known as an and an ampersand, right? So I add an ampersand here, like after the command that I want to run in the background. Now I press enter, it gives me this thing which is the process ID. This is the process ID, the process that got created when it was running this program, and this is the job ID, because this now became a background job, that is running. Now to view all the jobs that are running in the background, I can simply write the jobs command. I press enter and I can see that currently I have a job running called Python 3 and then test.py. Its status is currently running and its job ID is 1. And the plus simply means that this is the most latest job that has been created, right? If I, let's say, do a cat and then ampersand and I again do jobs here, right, then I can see that this cat that I just ran, its status is stopped because I didn't pass a value here, but it is still there. It's still, you know, in the logs, and the simple, job ID that it got was 2, and since it is the most latest, thing that is running, uh, the most latest job that I added in the background, this has a plus and this has a minus. Minus simply means that it is the second most latest job. If let's say I do a cat and then and I press enter and again I do jobs, I can see that this time I have two cat commands here. Both of them stopped. One has a plus, which means, and a job ID of 3, which means that this is the latest one. The other one has a job ID of 2 and a minus symbol, which means that it is the second latest one. And the first job that I created, Python 3 test.py, was it's still running. And the ampersand, what it did was that it simply just made sure that this is now running in the background and I can still run my terminal. Now if I, let's say, want to move a job from background to foreground, right? Foreground is like front, opposite of background. So I sent it to the background with the ampersand, but now I want to bring it to the front. So for that, what I can do is I can type FG, which is short for foreground, and I can simply press percentage, and after percentage I add the ID of the job that I want to bring to the foreground. So in this case, the Python 3 test.py that I ran is going to come in the foreground. So it says that this is what you were running in the background as the job ID of 1, and now it is running as it should have been. Now let's say that I ran this thing again, Python 3 test.py, right, and I ran this, right, but now I know this program is going to take a lot of time and I don't want to wait around for that much amount of time that this program is going to take. So what I simply want to do is I want to now send it to the background, right, after running it. And I don't think that it's making a lot of sense to interrupt this program or close this program and then run it again. I simply, it has already been executing for 5 minutes. I know it's going to take maybe 5-10 minutes more, but I don't want my 5 minutes to get wasted, so I just want to send it to background from here. So to do that, what you can do is you can simply press Ctrl Z, right. Ctrl C is what interrupts the program, control plus C, right, and control Z or control Z, right, the Z that I have typed, control Z, it is going to stop the program, right. Now I know this program is stopped. If I want to send it to the background after this, right, I ran this command, right, I pressed the control plus Z after it, and now if I type BG, I press enter. Now I know that this command has moved to the background, right. So if I again do jobs now, I can see that it is running in the background. Now let's say that I sent this command to the background, but I want to kill this, right. So there are two ways of killing it, right. The first way is that I bring it to the foreground, right, and I close it from here, right. The second way to do this, and now just to show you again, is that I can enter jobs. I can see that I just have two jobs there. I do a Python 3 and then test.py. I do a control Z, I do a BG, I check my jobs and I can see it is added. Now if I want to kill it from the background itself, I don't want to bring it to the foreground, but I want to kill it from the background itself, I can simply do a kill and then %4, right. This will kill it in the background itself. Now if I do the jobs again, I can see that Python 3 test.py was added in the background, but its status is now terminated, right? So that's how it usually works. That was pretty much it for this video. Now in this video we have talked about processes in a lot of details, and there are still a few things that we still haven't discussed yet, things like devices and file systems, and what is a bootloader, what exactly is a kernel, what does it do, things like that, right? So you can expect that in the next video, all of those things, where we are going to actually talk about Linux internals. Post that, we are also going to get started with some HTML videos where we are actually going to start exploring the basic front end things, and we'll start building a lot of things. So you can also expect that. And I hope you got to learn a lot of things in this video about processes, right? And whatever you learned, do make sure to write a blog or a nice Twitter thread about it. Tag me in it. Apoorv tweets as my Twitter handle. Tag me in those tweets when you share it with other people. Learn in public, right? Use the hashtag learning with Apoorv. And do make sure to subscribe to this channel, like this video, share it with your friends, the playlist, because now we have a lot of videos in this playlist, right? So anyone who would start watching it now would ideally be able to catch up with whatever we have covered so far. Learned in public, right? Write a nice blog and Twitter threads about it. I'll be taking a look at all the blogs and Twitter threads that you may write, and the good ones, the best ones out of them, I would be including in the Virtual Tech School's website. The website for Virtual Tech School is going to be revealed soon, right? So also stay tuned for that. And with that being said, I'll see you in the next video. Till then, bye.